Okay, good morning once again one and all. So in the last lecture we started designing a Cotter joint to transmit the axial tensile load of 50 kN. So in part 1 we selected a material, part 2 we selected a factor of safety, in part 3 we calculated all the design stresses, that is the safe stresses, we can call allowable or permissible stresses, right? In part 4 we calculated the design dimensions of rod D based on the tensile failure of rod. Then in part 5 uh, we done the stress analysis of a spigot and find out the dimensions D2, D3, D1 and A. So this is what up to the part 5 we have finished in the last lecture, right? So then in today we'll start with the part 6. So what is part 6? So part 6 is nothing but a design of socket. So the first component already we have designed, that is a spigot. Second component the socket. Now in socket, first of all let us see what we have to calculate, what we have to design. The first one is D1. So what is D1? D1 is nothing but the outer diameter of socket. Okay, and then D4. D4 is nothing but the outer diameter of the socket collar, and C is nothing but the thickness. So these three things we have to find out. Okay, so basically let's start. Now first of all, as I said that when the plane of the failure is perpendicular to direction of the force, the failure is tensile strain. So now what is a weaker section? This YY, this YY is nothing but a weaker section, you can see here. Okay, this section is nothing but a weaker section, a section where there is a hollow portion in the socket where the spigot is fitted inside or inserted, right? So that is the weaker section. Now because of this force P, what will happen? This tensile failure will due to the tensile stresses, this socket will break into the two pieces. Okay, you can see in this figure also, in this figure, or in this figure also. Okay, so first of all we have to identify the section. So this section YY is nothing but a section where there are more chances, or you can say the maximum chances of the tensile failure of the socket. Okay, so to avoid that, let us find out the area resisting the tensile failure. So what is the area resisting tensile failure? This is the area. Okay, this is the area which I have shown by the hatching lines. Okay, so this is the hollow portion, so we have to minus this, and this is nothing but the hollow rectangular portion, we have to minus this. Okay, so now, so you can see this red color area. So this red color area is nothing but the only area resisting the tensile failure. It is very easy to calculate how. So this outer diameter of the socket is nothing but a D1. Inside diameter of the socket is nothing but a D2, which is equal to the outside diameter of the spigot. Okay, so D1 minus D2, if you do D1 minus D2, you will get this hollow portion area. Okay, so you will get this area. So you will minus this area. Okay, but we have to minus this rectangular area also. Okay, so obviously how will you minus this rectangular area? So what is this thickness? This thickness is nothing but the T. Okay, so obviously this thickness will be equal to the thickness of the Cotter. Okay, because Cotter is inserted in the socket. Okay, so now how will you find out the area? So the area resisting the tension will be pi by 4 d1 square minus d2 square. This will be the circular cross section area minus how will you find out the rectangular area? How will you minus the rectangular area? Okay, so I want this much and this much only to be minus. So how I will minus? So total length is obviously this total distance of a rectangle will be equal to d1 minus this middle portion we have to minus, that is a d2, and what is the thickness is nothing but the T. So pi by 4 into d1 square minus d2 square minus d1 minus d2 into T will be the area resisting. So from this we will get this only the, so I am interested only in this red color. Okay, I have to minus this rectangular portion as well as this circular portion, because that is not the area which is resisting the tensile failure. Okay, so area resisting the tensile failure will be what? So I have again highlighted, you can see this. Okay, so this all cross area I have to minus. Okay, so how will I minus? d pi by 4 into d1 minus d2 square circular cross section area, and this rectangular area how I will minus total this length d1 minus d2 into this t. Okay, so this is nothing but the area resisting the tensile failure. Now once you find out the area, what is so what will be the tensile stress induced at yy, which is nothing but a weaker section of a socket. So this yy is nothing but a weakest section of the socket. Remember this, weakest section of socket, okay, where there will be a tensile failure. So sigma t is equal to p upon a. So sigma t is equal to, just will cross multiply. So p is equal to sigma t into area. Okay, just will cross multiply. So we have to solve the equations here once again. So p is 15 to 10 is 3, sigma t allowable 150, area pi by 4, d1 square minus 25, d1 we have to find out, d2 25 we know, okay, and thickness 8 we know. Okay, so this we have already calculated in the last video, that is the design of spigot. So from this you will get a d1 which is equal to 33.75, let us round up 35 mm. So d1, which is nothing but the outside diameter of the socket, is equal to 35 mm. So once I got, by doing a tensile stress analysis, d1, okay, the remaining we can find out from the empirical relations. Okay, so now let us first of all check that for this d1 is equal to 35 mm, let us check the induced shear stresses. Now where the shear stresses will induce. Okay, look at this three-dimensional figure. So basically try to one point you try to understand, that whenever you want to find out the tensile strength, you have to consider the perpendicular plane. So look from the front view. Okay, look in this manner, front view. So whenever you are looking from the front view at this three-dimensional figure, you can easily understand what is the area resisting the tensile failure, because once you understand the area resisting the tensile failure, the formula is very single, sigma t is equal to p upon a, or tau is equal to p upon area. So the important thing is to find out the area, because p and sigma t and tau are already calculated and constant. Okay, so remember that, look from the front view, talking about the engineering views. Okay, you will get a tensile failure. Similarly for side view, for shear failure, look from the side view. Okay, side view. So from this you can see that what area will be sheared. Okay, so whenever you are looking from the side view, you can see this much area will come outside, means what, this much area will come outside, but again this middle portion is hollow, because here there is a rectangular slot, so obviously that middle portion, as well as the circular cross sectional slot, so this middle portion will be a hollow portion. Okay, so obviously whenever you are looking from the side view, you will understand the dimensions. Okay, so this small rectangular portion and this small rectangular portion will come out, means what, it will shear. Why it will shear? Because of this p, that is a tensile force p acting on the socket, and here since it's a hollow portion, it's a weaker section, there are chances that this area having a length c, this is a length c na. So when you look from the side we will see this length c, so this length c will get sheared. So not only length c, this length c and multiply with total distance. What is this total distance? d4. What is d4? Outer diameter of this socket collar, and hollow portion is the inside, which is equal to d2, that you have to minus. So what will be the area? What will be the area resisting the shear? Obviously there will be a double area, this side also and opposite side also. So area resisting will be d4 minus d2 into c. Okay, so understand the views. From the front view you will get an area resisting the tensile failure, from the side view you will get an area resisting the shear failure. So what is the area resisting the shear failure? d4 minus d2. Why I have to minus d2? Because this is only the portion of rectangle we have to consider. Okay, is it clear? So d4 minus d2 into c, right? So from the side view I have got. So let us move on to the next point. So see, here you can see d4 minus d2 multiplied by c will be the area resisting the shear failure. So d4 minus d2 into c. Now once you find out the area resisting the shear failure, okay, it is very easy to find out. Now diameter of a socket collar d4. Now basically this diameter of a socket collar d4 is again calculated using empirical relations. So you have to remember these empirical relations, or you will find it in the PHG design data book 7.13 7.140. Okay, clear. So D4 we have considered 24 2.4D, that is equal to 2.4 into it 53 mm is the D4, and D2 we have already calculated inside diameter of the socket or diameter of the spigot. C also I have already calculated. What is C? I have calculated C is equal to 17 mm. In the last video I have calculated. Okay, I will write here how we have calculated the C. So we see somewhere it is required. I think the C was required somewhere in, it was required, yeah, it was required in the shear failure of the spigot. So we have calculated C as C is equal to A as 0.75D. Okay, clear. So from this, what is the shear stress? Tau is equal to P upon area. Okay, P upon area. So let us see whether this dimension D1 is sufficient for not. So D2 into D4 minus D2. So from this I am getting tau is equal to 52.52 Newton per mm square, which is allowable 0.70. So the shear stress induced in the socket, which will shear this rectangular portion of the socket, is 52.52, but it is less than allowable. So our design is safe for the shear failure. So same process we have adopted for the spigot as well as the socket, right? Tensile failure and the shear failure. Now crushing failure. To understand a crushing failure, try to look from the top view. Try to look from the top view. So from the top you will understand that, let us say this is a portion. This is a portion having a thickness T. Okay, this is a portion having a thickness T, because thickness T is equal to thickness of Cotter. Okay, so and if you look here, okay, and deep down it will go where? Deep down it will go up to the here. This total height will be equal to D4. Okay, so total D4 and this total, yeah, I will make it once again clear. Yeah, it will be like this, na? Look from the top view. Okay, so this total, this will be thickness T and this will be, let us say, D4. Okay, so whenever you are inserting a Cotter inside this socket, whenever you are inserting a Cotter inside this socket, you can see that at this area, which is D4 multiplied by T, what will happen at this area? Look from the top, on both sides you can consider. Okay, what will happen? Sigma C and sigma C. So whenever looking from the top at this area, which area? This T multiplied by D4, this area T multiplied by D4 will be the stresses or the crushing stresses acting on the socket area or the socket end. Okay, so whenever you're looking from the top, you'll understand how the crushing stresses are acting. Okay, now but the thing is that this D4 is not continuous, because this D4 is nothing but a diameter of the socket. Okay, so in between there is a hollow portion called as a D2, which is used to insert the spigot. So obviously what will not have this portion. Okay, will not have this portion. Let me make it correct. So we'll have only this much area. Okay, we'll have only this much area, right? So on this much will be the area where the crushing stress is acting. Which area? This area and this area. Okay, so I'll show you one more figure. You can see here. Okay, so imagine that you are looking from the top. Okay, you are looking from the top, you will understand more. Okay, so only this area and this area will be the crushing stresses acting. So what will be the area under crushing? The area under crushing will be D4 minus D2 into thickness T, right? So this will be the area under the crushing. So I hope you have understand how to calculate the crushing. So looking from the top you will get a crushing failure, looking from the front you will get a tensile failure, looking from the side you will get a shear failure. Okay, so calculate this. So sigma C is equal to P upon projected area, P upon D4 minus D2 into T. so getting a higher one 2 to 3.21, but what is our allowable crushing stress? 300. So it is less than the induced one, greater than the induced one. Means what? Induced crushing stress is less than the allowable one. This is the induced, or you can also call it the actual, and this is allowable. You can allow. So crushing failure of socket. So design is safe in the crushing failure. Okay. Now last but not least, design of Cotter. Okay. So we'll design this Cotter having a width B. Okay. Then thickness T. So thickness T, already we have considered the empirical relation for thickness T. Okay, and this is nothing but the length. So let us find out the remaining dimensions, that is a B. Okay, so the Cotter thickness is determined using an empirical relation and is proportional to the 0.31 times of diameter, right? So this we have already done in the later initial analysis. So now we have to calculate the width of the Cotter by shearing and bending considerations. Okay, so let us understand. So first of all, double shear of Cotter. Now I have already explained you that, yeah, you can see this area resisting the double shear, that this is the P by 2 and P, the forces acting on the shear. In free body diagram I have already explained. So this Cotter will get shear at this place here and here because of these forces. These forces are nothing but equal and opposite reactions of the forces acting on the Cotter socket end and the spigot end. So in this way you can see that, yeah, you can also understand. See, this is a plane of failure. This is a plane of failure and this is the direction of force. So direction of the force and the plane of failure are parallel to each other, you can see. So in such case the failure is always a shear failure. So what is the area resisting the shear failure? This area, red color area. This red color area is nothing but this area, which is nothing but the T into B, because this is B and this will be T, right? If I draw this plane T into B, so T into B is nothing but area. Just we have to consider the double shear because it is shearing at two areas, two ends, two portions, sorry. Okay, so how will you calculate the area resisting the shear failure? B into T, you can see this area I have highlighted here. This is called as the area resisting the shear failure. Okay, area resisting the shear failure. Now tau is equal to P upon area, that is a basic formula. So P upon twice B into T. Why twice? Because double area. Okay, so from this you will calculate a B. So what is B? B is equal to 42 mm. So now the dimensions B which you have calculated is based on the shear failure analysis. So as I have said you in the knuckle joint, that this B joint, the dimensions of B, which is equal to 42 mm corresponding to the thickness T, may be sufficient, may be safe for the shear failure, but it may not be for the bending failure. So so we have to also design the bending B, calculate the B based on the bending failure. Now basically what happens when the Cotter is tight in the socket and spigot, it is subjected to the shear stresses. But when this Cotter is loose, okay, during the operation the Cotter will become slightly loose. So when it is loose, the bending occurs. Okay, now what I have done, this is your Cotter now. So I have considered, I have placed it horizontally. I place it horizontally for doing some strength of material analysis. Okay, now the loading is assumed to be uniform in the spigot portion. Uniform in the spigot portion means what? This between portion where there is a spigot. Okay, means what? This portion is the portion of a Cotter which is inserted inside the spigot, right? Rectangular slot of the spigot. And secondly, the loading is assumed to be triangular, means this portion is nothing but a triangular. So this is a portion where the Cotter pin is inserted inside where? Inside the socket. So this is the socket portion and this portion is nothing but the spigot. Now I will not go into the detailed analysis because the detailed analysis I am writing here of this I have explained you in the part 2 video of knuckle joint, because that will be same, right? How I have used the storm concept. So for this you can use this. I'll explain you the basic one here, but detailed analysis you will find up in the part 2 video of knuckle joint, right? So I hope you understand. So this is a triangular portion, and this is a triangular portion, and this is the uniform portion. Okay, one second, just hold on. Okay, so already I have explained you that for this triangular portion, let us say this is the triangular portion. Okay, so for triangular portion, let us say this distance is, so let us say at this particular point the force is acting is p by 2. Okay, so let us say this is x and this is y. Okay, so from this what we will get, from this what we get, right? So we are from this side, we are considering it as a 2/3, and from this side we are considering as a 1/3. So this detailed analysis I have explained over to you there. Okay, so here we will understand. So similarly for triangular portion, for this portion, what is x? X is nothing but this distance. Okay, this distance. Okay, this x is nothing but a 1/3 of y, because we are considering from this side of the triangle. So SOM concept. Okay, x is equal to 1/3 of y, right? And so now what is this y? This y is nothing but the d4 minus this d2. Okay, because I want this distance. Okay, I want this distance total. Once again I will make it clear. I want this distance y. So y is equal to obviously this d4 minus d2 divided by 2. Okay, d4 is y I want na. So y I want d4 minus, I will minus d2 divided by 2, I will get this y. Okay, this is for the triangular portion. So I am getting x is equal to d4. What is x? X is nothing but this distance. Okay, see, it is like this. This is a triangular portion. This total distance for the triangular portion is nothing but a y. Here somewhere the force p by 2 is acting, and we have considered this x. So we have to find out this distance x, because the bending moment is maximum at the center. I am again requesting you can watch for this the detailed videos of a knuckle joint, where I have explained you from the basics itself. Okay, so x is equal to d4 minus d2 upon 6. I have found out this. Now what is z? Okay, this p by 2 from this center line, this p by 2 is acting at a distance z. Okay, so what is z? This z is equal to half of this d by 2, this distance d by 2. So this, in short, it is d by 2 of 4, right? So in this way we calculate x and z. Now once you have calculated x and z, now let us find out the maximum bending moment. Now we know that bending moment is maximum at this center, right? So how will you find out? So once you consider p by 2 acting upward, and once you consider p by 2 acting downwards, and take a moment is nothing but a force into distance. So p by 2, so this p by 2, what is the center portion? This is the center. So distance between these two dots. So p by 2, what will be the distance? D by 2 plus d by 2 plus x, because distance between these two dots is nothing but a d by 2, and this 1 and 2 distance is d by 2, 2 and 3 distance is x. So total distance of force P2 from the center. Why? Because maximum bending moment is at the center, d by 2 plus x. Similarly, consider this force P by 2. What is the distance between these two dots? Z. Okay, it's a very simple. Okay, so one is opposite, other is opposite to each other. Okay, so one is clockwise, one is anti-clockwise. So now we know what is x, d4 minus d2 upon 6. We know what is z, d2 upon 4. Okay, so from this we'll get a final for MB. So calculate MB. So bending moment, which is maximum at the center, is 272.916 into 10 is to 3. And now we will calculate the bending stresses by using the formula which is available on page 7.1, which is mb upon I into y. So again, now very important point. So what is sigma b, we'll understand later on. mb we have calculated, y, okay. Now try to understand that this is a rectangular portion, right? The Cotter joint is not a circular portion. So I is equal to, okay, what is I? That is a mass moment of inertia for this portion, which is having thickness t, and width b is nothing but a tb cube by 12, okay. And y, which is nothing but the distance from the neutral axis to the maximum distance from the neutral axis to the extreme fiber, is equal to b upon 2, okay. So same analysis we have done for the knuckle joint itself. So calculate sigma b. So sigma b is equal to 116.3, which is less than obviously sigma t, okay. So we can say that the design is safe in the bending, right? So we can say that whatever the dimensions we have selected for the b, which is equal to somewhere around 42 mm, is okay for the bending moment also. So this Cotter pin will not fail for the bending as well as the shear failure. So I hope you have understand the design of Cotter joint, okay. So now next you can solve, you can draw this diagram, give all the dimensions, and do the modeling in Fusion 360 or SolidWorks. I hope you understand. So this particular part, there is a bending in the Cotter. I have explained you fastly, but for the detailed analysis you can watch the video of knuckle joint itself, okay. So I hope you have understand the design of Cotter joint, okay. So thank you so much, and you can watch this video again and again to help, which will help you to understand the design of Cotter joint. The design of knuckle and the Cotter joint are almost similar, the steps are similar, slightly the components are different, okay. In knuckle joint we have a knuckle pin, in Cotter joint we have a Cotter pin, okay. Cotter pin is having is a rectangular portion having a thickness t, width b, and length l, okay. So thank you so much.